Let's talk about the names that we give to the different parts of a transistor and also talk about some design related details about it. We will take NPN transistor as our example, but the same will hold true even for a PNP. So we'll just take one example and work with it. Now the names given to these three regions are really based on their functions, what they do when you take your transistor and make it work like an amplifier. In a previous video, we've seen how this transistor can behave like an amplifier. And so if you need some refresher, it would be a great idea to go back and watch that video and then come back over here. But we saw in the previous video what we did. We made some connections. We connected this side to the ground. We had connected this side to, I think about a positive of 5 volts. Any voltage is fine here. And over this side, we had connected about positive 0.7 volt. And to quickly recall what happens, you see because of the forward bias over here, the P side is connected to the positive, the electrons are emitted from this junction all the way into this junction. And before they have any time to recombine, because of very small amount of holes over here, most of them just get swept across and collected over here. That's because of the voltage, that positive voltage we have supplied over here. So based on that, we can actually see the names behind this. Since this is emitting electrons, we call this region as the emitter. So this is called emitter. And since this is the region that collects the electrons, we call this as the collector. And this thin region in between is called the base. So the three parts of the transistors are emitter, base, and collector. And notice, in order for amplification to work, if you want to make this work as an amplifier, then the necessary condition that the two junctions must follow is that the emitter base has to be forward biased. This has to be forward biased. And the collector base, look at what's happening to collector base. It is reverse biased because notice the N-type is connected to more positive than the P-type. So this junction has to be reverse biased. This is a necessary condition. And we'll see what happens if you don't forward bias this. If you reverse bias the emitter base junction, then majority charge carriers can't diffuse through, and as a result, these electrons will not get emitted, and nothing will happen. And similarly, the collector base junction has to be reverse biased because these injected electrons have to get swept across. They can only get swept across. Remember, these injected electrons in this region act like the minority charge carriers. In the P-type, electrons are minority. And for them to get swept across, we need a reverse bias. We've spoken about this in previous videos, all right? And similarly, if you had forward biased it, what would have happened? Well, if you had forward biased this junction, first of all, it would be hard for these electrons to get swept across. But more importantly, the electrons from the collector would start diffusing into the base, and as a result, the net flow of electrons from across upwards, from base to collector, well, that would be decreased, right? Because there'll be some flow this way, and there'll be some flow this way as well. And so we'll just mess up with our amplifier working. And therefore, we don't want this region to be forward biased. All right, now we may have one question in your head. Isn't the collector and the emitter identical? If we were to flip the transistor upside down, it won't look any different. So what's the difference between them? Well, from the operation point of view, there's no difference. However, if you look from the design point of view, there are certain differences. And here are some of them. First of all, since the emitter's job is to, inject electrons into the base, we would like to dope the emitter very heavily. So emitters are always heavily doped. Heavily doped regions. And the idea is the more you dope them, the more electrons get injected when you forward bias it, and so more electrons could get collected, and as a result, you would have more amplification. On the other hand, look at the base region. The base region we have already seen. For proper working of a transistor, it has to be thin, very thin, very thin and lightly doped, very lightly doped. Okay, now what about the collector? Well, if you think about it, the collector doping doesn't really matter for us, right? I mean, look at in our amplification, what matters is how many electrons get injected, and that depends upon the doping of the emitter, and how many electrons recombine. That depends on this, right? The electrons that don't recombine will eventually get collected regardless of how many electrons are there in the collector. So strictly speaking, you can, whether you dope collector very heavily or you dope it very lightly, it's not going to affect our mechanism all that much. Now, having said that, there is one thing we need to take care of. You see, this PN junction is reverse biased. And we've seen before that when a PN junction gets reverse biased, if the voltage exceeds a particular value, it undergoes breakdown. That means a very high current starts flowing from N to P. We don't want that to happen. If that happens, that'll mess up with our amplification action. We don't want this junction to ever undergo breakdown when our transistor is working as an amplifier. So what we have to do is we have to make sure that this junction has a very large breakdown voltage so that it can withstand a lot of voltage before undergoing breakdown. Let's just quickly write that down. We need the collector base junction. We need the CB junction to have large reverse breakdown voltage. We usually call that as VR. So how do we achieve that? Now here's a simple way to think about it without getting into too much details. The lesser you dope this region, because this region is already very lightly doped, so the lesser you dope this region, the larger the breakdown voltage. I like to remember our Zener diode. Remember, Zener diode is very heavily doped, and under such heavy doping, it has a small breakdown voltage. That's a specialty. Well, lighter doping means larger breakdown voltage. So if you need more clarity on how that happens and how the depletion region gets affected, it would be a great idea to go back and watch that video on Zener diode again. But anyways, so to make sure that this reverse breakdown voltage is high enough, the collector is usually lightly doped. You get that? It's nothing to do with our operation of amplification, but just to make sure it doesn't undergo breakdown. So this is lightly doped. Now you may ask, well, how lightly doped is it? And this is not really all that rigorous. It depends on different transistors. It turns out that in some transistors, the doping concentration of collector is moderate between that of the emitter and that of the base. Well, in some other cases, it's seen that the collector doping is even kept smaller than that of the base. So there is no hard and fast rule, but what is important is that the emitter must be heavily doped and the base has to be thin and very lightly doped. The collector doping is only to ensure all these other design related issues, all right? So to make it visually more accurate, let me show a little bit less electrons in the collector compared to the emitter. One more difference between emitter and collector is in their size. It turns out that the collector is very big in size. Alright, so to be more visually accurate, it would be better to draw our transistor a little bit big. And that's what you will see in most drawings. You will see that the collector is usually drawn bigger than the rest of the regions of the transistor. And again, this has nothing to do with the amplification action. It's again from a design point of view. The idea is roughly this. You see, we want the transistor to be big enough so that when the currents are flowing through it, it doesn't heat up very quickly. If it's very small, its temperature will shoot up very quickly, and again, we can have problems. Emitter, well, we can't make that region big because, we want to make it heavily doped. So it's easier to dope something very heavily if it's small. Base is anyways very thin. It has to be thin for our amplification. It's the collector that really doesn't matter how much you dope it. And since we are moderately or lightly doping it, we like to make the collector big. Another reason for collector being big is that's the design. So this is not what a real transistor, a practical transistor would look like. In reality, a transistor would look somewhat like this. You ready? Here it is. A real transistor looks somewhat like this. This is how the design is for a real transistor. So you again have the emitter. Notice how small it is. You have the thin base region, and you have this huge collector region. And the terminals are over here. So this will be encapsulated, and you will have 3 wires coming out from here so we can do our attachments. And so collector is usually moderately doped, and it's also one of the biggest regions of our transistor.